All right, now I get to see if I can type my password under pressure. Good morning, everyone. Welcome to AngularConnect Day 2. I'm so excited to be here. This is one of my favorite Angular events of the year. I love coming to it. Coming to this conference feels like going to an Angular family reunion. I just see so many familiar faces. People come up to me, tell me, oh, I remember you from last year. We talked about this or that. I love interacting with our community here. And I'm really excited to be here to tell you all about Ivy. So for those of you who don't know me, my name is Alex Rickabaugh. I'm an engineer on the Angular core team. And I've been on the core team actually about as long as I've been coming to this conference, like 3.5, almost 4 years now. I've worked on a few things in my time on core. I worked on HTTP client, the Angular Common HTTP library. I worked on our service worker as part of our progressive web apps effort. And most recently, I'm working on maintaining the Angular compiler and getting it ready for Ivy. So before we get started, to really understand what Ivy is, you kind of have to have a good mental model of how Angular works under the hood. Many of you kind of already know this, so in that case, it'll be a refresher. But you can think of the Angular part of your application as being composed of two parts. The first part is the code that we generate when you run NGC, our AOT compiler, against your templates. You may have encountered that code before in the form of ng factory files. And the second part is the code in Angular itself that you import from core and platform browser that supports your compiled templates at runtime. And we call that part the runtime. And so these two together form what we call the Angular render. Now, on the Angular team, we get a lot of feedback from you, our users, through a variety of channels. You file GitHub issues, bugs, feature requests. You talk to our developer relations team, maybe directly through your company, or you fill out our developer survey that we had recently. And a lot of this feedback is specific. This doesn't work, this could be better. But there are some general themes there. You want Angular to be simpler. You want it to be easier to use and pick up and understand. You want builds to be faster. You want bundles to be smaller. And you want more advanced features like higher order components. And so we've continued to work on the framework and optimize it across all of these dimensions. But as we're doing this, we started running into some limitations. Our current rendering architecture, which is known as the view engine, just kind of wasn't getting us where we wanted to be. And so it was time for a new approach. And Angular Ivy is that new approach. At high level, Ivy is a new backend for our compiler, coupled with a new runtime. And together, they replace the view engine in your Angular applications. And we're doing this, it's a substantial refactoring of how Angular works internally. But just like when we released View Engine in Angular 4.0, it's going to be backwards compatible with existing Angular applications. For the vast majority of our users, you'll turn Ivy on, and your application will be better. And that's all really you'll have to notice. So Ivy has a few different design goals, but it has one overarching theme. And the overarching theme is that it's a simplification of how Angular works internally. With Ivy, we've been able to remove a lot of complexity from the framework, from how we compile applications, to how we package and bundle and ship libraries on NPM, to how those parts link together and depend on each other at runtime. And simplification is always a good goal to have in and of itself, not just because it makes things simpler, but also because you get a lot of benefits from it that you may not even anticipate when you start such an effort. And we've definitely noticed that with Ivy. So in addition to making Angular simpler, both to use and to understand, we had a number of other goals that we set for ourselves when we started designing this thing. I specifically want to focus on 3 of them. And the first one is optimizability. We wanted to make Angular code, both the code that we generate for your templates and the code in our runtime, more optimizable. JavaScript tooling has actually come a long way since we released Angular 2.0, and we want to take advantage of the best tools the ecosystem has to offer. And next, we wanted Angular compilation to be incremental. And this brings 2 benefits. It makes compilation faster, but it also reduces the burden on libraries to ship complex metadata to NPM for their dependents to use. And finally, while we're doing this, we wanted to make sure that Ivy would give us a flexible technical foundation to build all of the Angular features that you are all requesting. So we're going to dive into all of these goals and see how the Ivy design meets them. And I'm going to start doing that by talking a little bit about where we're coming from. To get the best perspective on Ivy, we need to understand how Angular has worked in the past. And so we're going to look at the two previous rendering architectures, the template compiler from Angular 2.0 and the view engine that replaced it in 4.0 and is still in use today. And we're going to do that by examining this fairly simple template and see how it gets compiled from template compiler to view engine to Ivy. And this template is a little more complex than just hello world. We've got a couple elements. We have title being interpolated. We have a child component with an NGIF. This is a pretty good example of a typical Angular application using a few of our more common features. So the first one we're going to look at is the template compiler from Angular 2. 2.0 was released in September, just about 2 years ago and change. I honestly can't believe it's been that long. It feels like it was just yesterday. We had 4 major versions now. Back then, I was working on platform bootstrapping APIs, things like how the application ref gets created under the hood when you call platform browser. And I remember going to team meetings and tech talks and listening to Tobias tell us all about his new AOT compiler and some of the things that it could do. And I never imagined that I would be up here talking to all of you 2 years later about how I'm helping build the same things for Ivy. So the template compiler in Angular 2 compiled HTML templates into generated JavaScript code to both render and change detect them at runtime. And so I went on NPM and I installed Angular 2.0.0. You can still find it there. I wonder if anyone's actually still using it. But I built this simple app with it using my example template. And I dug around in the ng factory file and pulled out this code. And this is the code that renders that template in template compiler. And it's kind of dense and hard to kind of look at, but you can kind of get a general idea of what's going on. On the left-hand side here, we have a lot of properties on the class that we're assigning DOM elements to. And this is so we can update them or delete them later. And on the right-hand side, you see calls to our renderer to do things like create elements and create text nodes. We're also creating the NGIF here towards the bottom, as well as a couple other Angular classes like viewContainerRef and TemplateRef. And this code is actually really efficient. We did a lot of research at the time to prove that this is one of the fastest ways to create DOM structure in the browser. And our benchmarks have backed that up. But something happened. As more and more developers started using Angular and building bigger and bigger applications with it, we started getting feedback that these generated templates were just too verbose. They were adding too many bytes, too much overhead to bundles. And so we needed to come up with a different approach that would allow us to represent templates with less overhead. And so for Angular 4.0, we went back to the drawing board and came up with the view engine. The view engine, unlike the template compiler, represents templates not as an imperative list of rendering operations, but as a data structure. And there's a runtime component which traverses the data structure to either create DOM nodes or execute change detection. And by doing that, we optimized our template size and managed not to sacrifice performance during rendering. So here's what a view engine template looks like. It's much smaller. It's also harder to understand because there's a lot more kind of magic numbers and nulls running around. But we can still get the general idea. We have a div and a span here. You can imagine the next line is a text node. And we still have our NGIF being created to control that child component. So Ivy is along the same vein. It's a replacement renderer for Angular. And it has the same fundamental moving parts. It has a template compiler, which translates HTML templates to code, and has a runtime, which supports rendering and change detection in the browser. And it's a replacement for the view engine in that the exact same applications can compile on Ivy as did before. And the Ivy team is actually hard at work validating that compatibility. We have hundreds and hundreds of Angular applications at Google, and we're in the process of testing Ivy out with them and running their thousands of tests and fixing any instances that we find where Ivy's behavior is different from the view engine before it. And so by the time Ivy is released, it will be validated by all of these tests at Google, not just our own internal test suite. So let's dig deeper. Let's take a closer look at how Ivy actually works under the hood and how it achieves all of our goals. So the central kind of design idea in Ivy is that Angular decorators, like @component and @directive, get compiled to static fields on the types that are decorated. So @component becomes @ngComponentDef static field. @directive becomes ngDirectiveDef, injectable and so on. And by doing this, we've actually taken the code that used to be produced in separate ng factory files, and we've moved it into the component and directive classes themselves. So here's what this looks like in practice. On the left here is our root component with our example template. And on the right is the output of what NGC generates in Ivy mode today. This @component annotation has actually become an ngComponentDef static field. You can think of it as the decorator @component actually has an effect, which is to patch a static field onto the class. And this static field contains metadata that tells the Ivy runtime important information about this component. Things like what are its selector, and the fact that it uses two directives here, the child component and NGIF. It also has, at the bottom, a template function, which is responsible for doing the same things as before, rendering the template to DOM, and then running change detection. And so here's what the Ivy template function looks like. And right away, you'll notice a few things. It's also pretty short. Unlike the view engine, it contains imperative calls, actually more like the original template compiler did. And these imperative calls are doing things like creating div and span elements, setting up the child template with its NGIF. The other thing you'll notice is that I've actually included the change detection code here as well. I couldn't fit it on the slides for the other ones, but for this one, the first if block renders the template the first time the component is inserted into the DOM. And the second if block runs change detection. So it's checking two bindings here. The first is our interpolation for title, and the second is the condition for the NGIF. Instead of a single template interpreter at runtime, like we had in View Engine, in Ivy we've broken that runtime up into a set of individual rendering functions that we call the Ivy instruction set. It's almost like an assembly language for Angular templates. And a template gets compiled to two sequences of these instructions. One sequence to create it and insert it, and the other sequence to run change detection. The instruction set is comprehensive. It covers not only things like DOM creation and data binding, it covers things like internationalization, styling, pipes, and SVG. So as an example, let's look at how DI works under the Ivy instruction set. So here's an example service class. This is an Authentication Guard for the router. It's going to check permissions on the current route when the user navigates to it. And it's injecting three different things. We're injecting the router, we're injecting the HTTP client, and we're also injecting some config object using @inject. And you can imagine our implementation of this guard might have logic like this. First, we check the config to see what permissions are required for the current URL. Then we use HTTP client to make a call to see if the user actually has those permissions. And finally, if they don't, we use the router to navigate them away. So what Ivy is going to do is it's going to take this @injectable and compile it to an ngInjectable-def field. And it looks like this. This ngInjectable-def has a factory function associated with it. And the factory function is responsible for actually creating the instances of this guard. And it works through two steps. One, for every dependency that needs to be injected, the factory function will call the Ivy inject instruction. It'll give the inject instruction the token, and it gets back an instance of the dependency. And once those instances have been created, all the factory function has to do is call the constructor like normal. And I actually found this to be interesting because this pattern is exactly how I imagine dependency injection in my head. Right? You're asking some injector to give you instances of the dependencies, and then you're just calling the constructor with those instances. Right? That's nice and simple. And another thing I'd like to point out about this is if the auth guard actually had no dependencies, right? If everything were hard-coded in its logic, then it wouldn't actually need to call the inject instruction. Our factory function would just be calling new auth guard, open parenthesis, close parenthesis. And that's not an accident, as we'll see later. So let's talk about the benefits before and the goals that we had for Ivy. There are 3 of them that I mentioned I was going to cover: optimizability, incrementality, and flexibility. And optimizability is one of the more important ones. Ivy lets us leverage a growing ecosystem of JavaScript tools that optimize code. And in particular, I wanted to focus on an optimization called Treeshaking. Treeshaking is what's going to take us to a model in Angular where if you don't use a feature in your application, you don't pay the cost of the bytes to support it at runtime. Treeshaking is one of those terms that gets thrown around a lot without really being very explicitly defined. So I'm going to attempt to do that here. And it also doesn't help that people call it by lots of different names. You may have heard it referred to as dead code elimination. Other people say no, it's called live code inclusion. They all refer to the same fundamental optimization, which is that looking at an application bundle, the optimizer attempts to prove that certain code is not used at runtime. And if it can do that, it can remove that code from the bundle and make it smaller. And the first time I heard about this, I had a little thought in the back of my head. It was like, well, where is that unused code coming from? As an application developer, I don't have time to write code that I'm not going to actually use in my application, right? I don't have time to be that inefficient. I have too much work to do. But as it turns out, there is a lot of code that ends up in bundles that doesn't necessarily belong there. And that's because we import things from libraries. And libraries are great, right? The material library has a ton of components that you can pick and choose from for your application. But it's very unlikely that you're going to use all of them. Right? There's just way too many for that. Your UI would be crazy. But the way ES6 works, if you put an import statement at the top of your TypeScript code that says import from Angular material, all of material by default would end up in that bundle. What the Treeshaker does is actually understand the code enough to go look through all of material and say, no, you're only using the material button and the material side nav, and the rest of it we can throw away. We don't actually need that. So in the ecosystem today, there are a number of tools which have emerged as capable tree shakers. The first one I ever used was Rollup. Rollup is an ES6 bundler, and it has the ability, while it's bundling code, to look and see which declarations you're actually using, which classes, which functions. And it can remove the ones that you're not actually referencing. Webpack 2 also shipped with tree-shaking functionality that was inspired by Rollup's design. One that I was surprised to see on this list is Uglify.js. Uglify is a venerable JavaScript compressor. Its job is to make your bundles small. And it does a number of optimizations to achieve that. And one of the optimizations it can do is actually dead code elimination. It knows how to remove code that's not referenced. So that's actually the tree shaking that powers the Angular CLI. We rely on an Uglify Webpack plugin under the hood to do that. And we actually have our own plugin we ship called Build Optimizer, which knows how to annotate Angular code to better tell Uglify what's used and what's not. And the last optimizer I wanted to mention is the Google Closure Compiler, sometimes known as JS Compiler. And this one is interesting because it actually produces the smallest bundles. If you remember, Igor yesterday in his keynote talked about Hello World and Ivy being 2.7 kilobytes. That's with Closure Compiler doing the optimization. One of the challenges with Closure Compiler, though, is that it requires you to write your applications in a very specific way. It's very strict about the type of JavaScript that you write. And if you stray from that, it tends to kind of break applications in interesting ways. So Closure requires, the benefits are amazing, but it requires a lot of buy-in in order to use it. Ivy, from the ground up, has been designed to be tree-shaken by all of these optimizers. That's the reason we broke the runtime up from this big interpreter into smaller functions, separate instructions that get compiled with your templates. So if you're building an application and you don't need to use internationalization, you don't get internationalization instructions included in your compile template. The tree shaker will notice you're not using those parts of the framework and can remove them. If you don't use content projection or SVG elements directly in your template, the Angular compiler will not emit those instructions. The tree shaker will notice you're not using them and can remove them from the bundle. And this happens across the entire framework. Core concepts like dependency injection are designed in Ivy to be tree shakeable. If you can write an application that doesn't have an application injector, right, that doesn't use DI at the ng module level, some simple applications might want to do this. And if you do, the tree shaker can remove those parts of DI from your bundle. This is a big improvement over what the View engine could do before. If you remember, the View engine consisted of a compiler that generated data structures and a runtime which traversed those data structures and interpreted them. And the problem with that is that the interpreter had to handle whatever template it got. We didn't know ahead of time whether you were going to use content projection, whether you're going to use internationalization or SVG. And so while we made that interpreter as small and as optimal as we could, fundamentally, the tree shaker could not break it up, could not remove parts of it. And there are other areas of the framework as well where tree shaking is difficult. One that comes up in particular is dynamic component instantiation. So this happens when you want to insert a component into a view somewhere, but you don't actually know which component that's going to be until runtime. And this tends to come up in cases where you're doing things like overlays, or tooltips, or modal dialog boxes, right? Where you have some part of your application that wants to render content, but you don't know what content until the rest of the app decides later. And so if you haven't done this in Angular, the way it works is you get this thing called the view container ref. And the view container ref kind of points to somewhere in the DOM where you can insert content. And then you take your component type that you want to insert, and you go to this thing called the component factory resolver. And you give your component type to the component factory resolver, and the resolver hands you back an ng factory for the component. And this is one of the cases in our APIs where factories have kind of leaked through to the user. Normally, we try to hide them. The CLI tries to keep them in the background and make sure you don't have to deal with them. But in this case, you actually have to get the factory in order to do something. And the trouble in this scenario is that this component factory resolver ends up not really being tree shakeable. And that's because it's essentially a giant map. It's a map of component type to ng factory. And the tree shaker looking at this map has no idea which component types you're going to look up at runtime. Right? How could it? Your application didn't even know. That's why you're inserting the component dynamically. And so the tree shaker has no choice but to see this code and say, OK, I just have to include all of it, right? Because anything else might break your application. And Ivy deals away with this problem entirely. Because in Ivy, we've taken what used to be in the ng factory file and put it in those static fields on the component. So when you have your component type that you want to insert, it already has all the information on it that the runtime needs in order to do that. You can just hand it to the view container ref, and on you go. So Ivy is going to enable us to simplify a lot of our APIs around factories. All of this focus on making Angular tree shakeable and optimizable has paid off. If you take a Hello World application, compile it with Ivy, minify it, compress it, you end up with a bundle of about 4.5 kilobytes. And Igor yesterday mentioned 2.7. That's with Clojure compiler. 4.5 is actually with standard kind of Angular CLI type tree shaking. We're pretty proud of this number. And a lot of people, when they hear this, actually this happened to me at the conference yesterday, tell me, okay, well that's great, but my application is not Hello World, right? So is this actually relevant? Does it actually matter? And there are two very good reasons why we care about this number, even though that's true, right? Most applications are not hello world. And the first one is, it gives us a really good metric for figuring out just how optimizable and just how tree shakeable we actually are. So if I'm sitting back and designing a framework feature, it's easy for me to rationalize and think, okay, most people are going to use something like content projection in their application. So it's okay if the code for content projection can't really be optimized away. Most applications are going to include it anyway. And that might be true. But if you do this across your entire feature set, now you've created a framework where nothing can be optimized. So what focusing on our hello world number does is keep us honest. It helps us meet our guarantee that most major parts of the framework should be optimizable, even if they're things which most applications use. And secondly, it turns out that this hello world example is actually representative of a real use case. We have Angular elements. And what elements allows you to do is take a component that you wrote, package it up and bundle it as a custom element, and then use it in an application that might not even be using Angular. Just drop it into an application somewhere else. And when you do this, you really want that bundle to be as small and efficient as possible. But also, it's very likely that the element you're packaging is not as complex as your average Angular application. Maybe you're packaging up something like a date picker, and you probably won't be using content projection. You might not be using dependency injection. And so with Ivy, we can actually optimize those Angular element cases and tree shake them down to a level where they actually work when you deploy them to another application. Ivy is very efficient at this. So Ivy is designed to be fully optimizable by the current suite of JavaScript tooling. The thing is, though, new tooling is being invented almost, it seems like, every day. I read about a new bundler or a new optimizer. And there are also optimizations which are known, certain optimizers can do them, but they haven't made their way out to the full tool chain yet. There's some things Closure Compiler can do regarding moving code around, for example, that would really benefit lazy loading, and we expect to see that in kind of other more commonly used optimizers eventually. And when that happens, Ivy will be ready for it. The second goal that I talked about, second main goal for Ivy, was this thing called incrementality. We wanted to speed up the compilation process dramatically. Both of Ivy's previous renderers, the View engine and the template compiler before it, use something called global compilation. And what that means is when you typed ng build prod into the CLI, it would run TypeScript to compile your application. It would run ngc, which would generate ng factories for the templates and other Angular types in your application. But ngc would also compile the components and directives in all of the libraries that you were importing, all of your dependencies. So we would compile those libraries during the application build. And this is in contrast to incremental compilation, where libraries get compiled and deployed on NPM, and by the time you import them, there's no work remaining to do. The application build can then only build the application classes that you're interested in, and you link them together and you're good to go. Right? The application and the libraries are compiled separately. A good way to think about that is if you use Material in your applications, Material is already fully compiled, ready to go when you npm install it. And it sounds like that's a much better world, right? And it would be. It's fairly difficult to get there, actually. To do it in Ivy, we've implemented a rule that we call locality on the team. And locality is pretty simple to explain. It means that when we're compiling an Angular component or a directive, and that component or directive depends on other Angular pieces, like its module or other components or directives, we can only refer to them using information that's known about their public APIs. That means that we have two really nice properties. One is that it will be safe to ship the code we generate to NPM. And the second is that we can actually compile them without needing to know too much about those dependencies. In fact, we can do it with the information that's in the DTS files. We don't need any extra metadata about the code. Now in Ivy, we actually add some information to the DTS files for the Angular public API, things like selectors, et cetera. But we can rely purely on TypeScript to pass this information along for us. So here's a simple example of locality in action. In Angular, your components can have inputs. And the name that your users bind to for the input does not actually have to be the same as the name of the field that the value gets written to on the component. You can think of the name of the input, the property name, the one you bind to, as public API, and you can think of the name of the field that it gets written to as an implementation detail. And in fact, it's possible for a component to change the name of its fields without actually breaking anybody using that component in their templates, because they've kept the property name the same. Which means that if you had a binding and you were to generate code like this, where you're writing the new value to the field directly using the field name, you're actually relying on part of the directive's private API. And that's okay, it's still going to work, but that means that any time that component or directive changes, we have to regenerate this code, because we have to assume that the name of the field might have been changed. Right? We don't know what the library author did when they published their new patch version. And that's one of the reasons why Angular today relies on global compilation, because we regenerate all of this code only once we know everything about your application up front. Another way you might imagine doing this is by only ever referring to that input by its property name, the public name. And you would probably introduce some function, here I've called it bind, which at runtime would look up on that component what field that property goes to. At runtime, we have that metadata, right? And then write the value out to the right field. And this code would be safe to ship on NPM. It would be safe to leave it in place even if the field name changed, because we're only relying on the input by its public API name. And in fact, this is exactly what Ivy does. When Ivy sees a property binding, it generates an element property instruction. And the element property instruction takes in the property name of the input and the new value, looks up in the directive def or component def which field that goes to, and then writes the value out. And that means that Ivy code is safe to ship on NPM. It's safe to build libraries in advance of the application. We don't need to recompile them every time you update their dependencies. So View Engine ran afoul of this in a lot of different places. Here's another example. This is our template from before, compiled with View Engine. And what I want you to focus on is this line here concerning the NGIF directive. And there's some magic numbers in here, but the DID function is a directive definition. And what I want you to pay attention to is the array in here, with view container ref and template ref. And these are the constructor parameters of NGIF that need to be injected, written into the template generated for our application. These are private API of NGIF. If NGIF is updated behind the scenes, like if the Angular team decides we need to inject something else, it wouldn't break your template, but it might break the code we generate for it. And that's why we only generate that code at the very end for application bundles. In Ivy, if you remember, these constructor injected parameters go into the factory function for the definition. So here's NGIF, which has directive def, and it has a factory function that's injecting its two parameters. And this code is safe to ship to NPM. It means that consumers who rely on NGIF don't need to know what its private constructor parameters are. NGIF has that information encoded on it. All they need to know to do is call its public factory function. That's locality in action. And you can think of Ivy, therefore, as providing a stable API for generated Angular code to be deployed on NPM and then consumed by other applications. And because of that, we took what used to be a big monolithic global compile and split it up so we can build libraries and applications that depend on them separately. right? And that not only builds things much faster, but also enables us to simplify how libraries are packaged. We don't need to ship as much metadata because we only rely on their public API. So Ivy builds are fast and incremental as a result. And the last benefit of Ivy that I wanted to talk about is its flexibility. The Ivy project in general has never been about delivering exciting new features on the day that we ship Ivy. Instead, it's been about taking the Angular that our users know and love and making it better, right? Faster compiles, smaller bundles, better debuggability. But at the same time, when we're undertaking this big effort, we wanted to make sure that our design would give us a foundation for building all of the cool features that we wanted to do and that our users wanted us to do, right? We wanted to make sure that our technical direction was good. And it turns out Ivy actually is really good at this. The instruction set makes us very extensible. We can take an existing Angular feature, which is compiled to a couple instructions, and we can write new instructions to implement that feature in a totally different way. And as long as we don't remove the old instructions, they'll continue to work. Existing code continues to work. And we can evolve the framework over time in a very clean fashion, right? If we're writing a new feature, it's really easy. You just introduce new instructions. There are some things, though, that Ivy does get us purely out of the box by the nature of its design. One really interesting one is a case of hybrid applications, where you have a mostly AOT compiled app, but you want to use JIT somewhere. Think of this as like $compile from AngularJS. So if you're willing to pay the cost of shipping the compiler to the browser, you can actually have a component which has its template generated at runtime, compile that with JIT, and then insert it into your AOT application, and the two can talk to each other seamlessly. Ivy does this as a direct result of incrementality. We've also been able to remove a lot of the complexity around NG factories. We still generate them, because applications still import them, but we generate shims that actually don't do much under the hood. And so in the future, we'll be able to optimize these APIs. We'll be able to make our bootstrapping API simpler. We'll be able to make lazy loading a lot simpler. Right now, really the only way to lazy load Angular code reliably with a good build story is with the CLI. And in Ivy, we think we can do better than this. And Jason, in his talk coming up, will actually show you a demo of this. And finally, NG factories have kind of been a stumbling point for users because we hide them from you in the beginning, and then all of a sudden you might encounter it in some situation, something you're trying to do. So we've been able to remove a major pain point from the library. And going beyond the kind of immediate future, you'll still be able to write templates normally, of course, as HTML. But you might imagine some components with complex or unusual views might benefit from having their templates handwritten in the Ivy kind of assembly language instruction syntax instead of being compiled and translated from HTML. And we're thinking about how we can create an ecosystem around this, how we can empower the library authors in our community to come up with interesting and powerful abstractions on top of Ivy's low-level APIs. One commonly requested feature, for example, is the ability to write higher-order components, which is a component that gets wrapped by a function, and the function kind of adds behavior or does something else to the component, and then you use that in your application. Ivy actually makes this possible, and we're thinking of ways we can do that. So it really does provide for us a flexible foundation for Angular in the future. Our team is deeply focused on making the Angular we have today more optimizable, making it compile incrementally, getting this foundation up and running. And once those are achieved, we have a long list of ideas that we want to investigate. So in summary, Ivy is a significant refactoring. It aims to simplify much of Angular's internal complexity. By removing the need for ng factory files, we can simplify our bootstrapping story, we can improve lazy loading, and we can get rid of a common user stumbling block. Our granular instruction set is making templates more optimizable and making the framework itself tree-shakeable. And through our switch from global to incremental compilation, we've been able to make builds faster and at the same time reduce the requirements on libraries, which is another kind of common pain point and stumbling block. And we're confident that our users will love these improvements to Angular, and we're working really hard to finish all of these pieces and get this into your hands to see what you can do with it. But if you can't wait for that, and you're interested to see kind of more of Ivy in action, I highly recommend going to Jason's talk immediately after the break in track 1, where he's going to show you some examples of applications running Ivy today in action. Thank you very much for having me. That's all I have for you.